Hi guys, this is 13D. This is another probability distribution. This one is called the normal distribution. This is the first of the distributions, potentially the last, which focuses on continuous information and not discrete outcomes. So, for example, we might be looking at the heights of everyone in year 13 or something or other. The formula behind this one is pretty nasty. If you have a little look at this one, which I'm focusing on here, and again, you don't need to know that for the exam. You certainly don't need to know it for this course. But there is quite a complicated formula here, which is coming up with the shape of the curve, which is this bell-shaped curve or Gaussian curve here. In terms of describing the distribution, we can say X is distributed normally, and in the brackets, we have our parameters here. We have our parameters mu, which is the mean of the distribution, and sigma squared, which is the standard deviation squared, which is the variance there. So sigma, this little Greek symbol here, so the lowercase sigma, is used for standard deviation in this case. Okay, so because we're talking about continuous data here, we need to work out the area underneath a curve. So we need to do integration essentially for this function here to work out the probability trapped between your two bounds, your lower and upper bound that you're interested in. Okay, but in reality, you don't need to do integration because your calculator will do all of this for you. Okay, let's look at a few examples. Where was I finding it? This one here, this is from, not this guy here, Statistics by Jim. This was quite nice. So it said, the normal distribution is the most important probability distribution in statistics because it fits many natural phenomena. For example, heights, blood pressure, measurement error, IQ scores, all of these things follow the normal distribution. In particular, when you're making measurements, for example, I don't know if you like measurements of heights of people in your year group potentially might have a mean and a standard deviation and might be centered around the mean symmetrically. Likewise, if you're talking about, I don't know, some filling up cans or something or other and measuring all of the exact weights of cans in a supermarket. Some might be overfilled, some might be underfilled. There might be an average. There's probably a standard deviation as to how far, which would show us how far away from the mean these things are distributed. In other words, how close to the mean or how spread out these things are, but normally within a bell-shaped curve. Okay, so let's have a look at this. So here's a little rule, which again, you don't really need to know about in this case, but it's kind of useful to know. This is the 68, 95, 99 rule, or often 99.7% rule. So this kind of tells us that if some measurement that we're taking is distributed using a normal distribution, if it's following this pattern, then you will get, if it's exactly normally distributed, then you will get 68% of all values will lie within one standard deviation of the mean. So what that means is, say, for example, here, if we've got, I don't know, let's do the heights example again. So heights in potentially year group, we could say are known to be normally distributed with a mean of 170 centimeters and a standard deviation. Let's say that sigma is equal to 10 centimeters. So that would mean that this would be 160 centimeters and this would be 80 centimeters, so 10 centimeters either side of the mean there. And that would then trap 68% or 68.27% of all of the information. And that's always true if something is following a normal distribution. So within two standard deviations of the mean, almost everything is caught. Almost all observations will be caught within two standard deviations of the mean. So that gives you a sense of what the standard deviation means. And of course, if the standard deviation there was instead 5 centimeters, then it would mean that this thing, the whole graph, would be much tighter in. And this would be 165 here, and this would be 175 centimeters. And then that would catch. 68% of all values. Okay, so these values here, this is always true if something does follow a normal distribution. However, if you're just talking about a sample, say for example, there are, I don't know, say there are 15 people in your class, and say then you try to work out the average of those 10 people. So the average might be still 170 centimeters high, but there may not be a single person who is in that category there of 170 centimeters exactly high. So when you've got a sample, it won't necessarily look like this. It might be a little bit like, well, it might be that there's just ones all over the place, or it might be that you put into categories and you get biggish bar here and a bar here, and different size bars which are kind of looking roughly normally distributed, right? So that's the difference between a sample with a low size for n and a population which we know to follow a certain distribution, and often we'll be told that in a question. Okay, so let's look at a question then. So I thought this time around it might be useful to look at a question from the book. So let's look at this one here. So let's look at example 10 from the book. This is on page 597. So this one says the lengths of trout in a fish farm are normally distributed with a mean of 39 centimeters and a standard deviation of 6.1 centimeters. Okay, so again, we're expecting that plus or minus 6.1 centimeters will catch about 68% of all fish either side of the 39 centimeters here. So part A says, find the probability that the trout caught in the fish farm is less than 35 centimeters long. So what we're looking for here is the probability that X is less than 35 centimeters long. Now, importantly, this does not need to be less than or equal to 35 centimeters because we're talking about continuous data here. So with the binomial and the Poisson distribution, we had to define whether or not we were interested in using the 35 or not. But in terms of this graph here, and it's always a good idea to make some sort of sketch. I'm not going to do a very good version now. I'm trying to do it live. Okay, so it's always a good idea to come up with a sketch here, and we could put in that's 39 centimeters. We know that roughly 68% is plus or minus about 6 centimeters. So 35 is going to be somewhere about here. And we're looking for the probability here, which is trapped over to this side. So we're looking for the size of this area here. So area is representing probability here. Now, when it comes to actually having your axis and finding your PDF, in this case, f of x, which was that horrible looking function I showed you a minute ago, that sort of has no real meaning in terms of the probabilities here, because of course the chance of you actually landing on 39 centimeters exactly, that's to say, or 35 centimeters for example, that's to say on this, exactly this is infinitely small. So there's no meaning to that height. The only meaning in terms of probability is the trapped area. Okay, because the trapped area represents your probability. So we're looking for this trapped area here, and all of the trapped area, of course, is going to sum to 1. Okay, so let's just take that back for a second. So find this probability. Well, we can go straight to our calculator here. In olden days, you'd used to use tables, and you'd have to transform your variable to transform it into the standard normal variable. But these days, we can just use our calculator, especially in IB. So we can go again to Scratchpad, to probability, to distributions. We can go to normal, PDF, or CDF. And you can see that there's inverse normal distribution in there. We need normal CDF. You will not be using PDF. So CDF says lower bound, what do you want to use? They already input in the TI Inspire, they input some incredibly small value for this. So you can put in minus 9,999 if you wish, or just go with what the calculator says. And the upper bound here is 35. We don't have to have the equals to there. And then they give you the two statistics. Now, there's two statistics I've forgotten to write down. The fact that this is normally distributed, in this case, X, is normally distributed with a mean of 39 and a variance or standard deviation squared of 6.1 squared. Now, really important, okay, that you know that they always use the standard deviation squared or the variance when they're writing things in terms of brackets. So if you're trying to get marks in an exam, you need to remember to put in your variance in this case, but also you need to know that your calculator only accepts the standard deviation. So if you're given this format in the exam, you'll need to remember that you're only going to put the square root of this thing here into your calculator, which happens to be 6.1 there, of course. Okay, so I'm putting in mean of 39 and standard deviation of 6.1 into my calculator. And I'm getting an answer of, for this one here, I'm getting an answer of 0.25, and then it's 5996. So I'm just going to say 256. You might want to write down, of course, more decimal places before you actually round off. I'm just keeping things simple here. Let's see if we can look at the answers to this one. So we're in, oh no, it's on the book, that one. So in the book, let's just check that one out. Yeah, so 0.256 is the answer. There we go, that's all sorted out. So part B says, now on part B, Cliff catches 5 trout in an afternoon. Find the probability that at least 2 of the trout are more than 35 centimeters long. State any assumptions that you make. Okay, so he catches 5, and we're now interested in whether 2 of the trout, or at least 2 of the trout, are more than 35 centimeters long. State any assumptions that you make. Okay, so this is another one of those where it's going to turn into a binomial distribution, because we're now interested in, let's call it y. We're now saying that y is binomially distributed with a sample of 5. So we've got 5 trials here, and we have a probability of success here. Now this was less than 35 centimeters long, and now they say 2 of the trout are more than 35 centimeters long. So we can simply use 1 minus this probability here to get the answer here. And again, remember, equals to 35 has no meaning, right? So we can just use 1 minus the probability from the question above. So we're going to use, sorry, the pen's not functioning at the moment. Let's just go on and off with this. So we can use 1 minus 0.256, and really better to use the exact answer there. I've lost my other decimal places there, but it is still on my calculator. Okay, so let's go for this one. So I'm going to do a Control C on this one. And now we want to know the probability in this case that y is greater than or equal to 2. So I'm going to go probability, so scratchpad menu, 5 probability, and then distributions, which is 5. We could go normal CD, go binomial CDF, number of trials is 5, probability of success is 1 minus Control V, my answer, which I just saved from scratchpad. And then the lower bound here is going to be 2, and the upper bound is 5. So let's press OK on that one. I'm getting an answer on this one of 0.98. My pen's playing up again. Okay, so that's 0.983 there, okay? Right, and just checking with the book on that one as well, you can see that they've done exactly the same thing. They've done 1 minus the probability from the previous part in order to get the 0.744 there, and that's what they're putting into the calculator. Right, okay, so for part C, let's just get rid of everything here for the moment. Okay, so for part C, it says find the probability that a trout caught is longer than 140 centimeters, given that it is longer than 40 centimeters. So you're asking for the probability of this I think I called it X, but they're calling it L now. So L, again, remember, is normally distributed 39 centimeters and 6.1 centimeters squared there, or 6.1 squared for the variance, rather. So we're looking for the probability that L is longer than 42, given that it's longer than 40. So longer than 42, given that the length is greater than 40 centimeters there. Okay, now remember the conditional probability formula. We've got probability of A and B, or intersection B, rather, is, what am I talking about? Probability of A given B is probability of the intersection of the two of them divided by the probability of B. Okay, so in this case, we want the probability that L is greater than 42 and also L is greater than 40. Now, the intersection of those two things is just the length is greater than 42. Okay, so the overlap there is just when the length is greater than 42. So we actually don't need to worry about that second part. We can just say that L is greater than 42 divided by the probability that L is greater than 40. Now, both of these two things here, you'll get from your calculator by doing normal distribution CDFs, starting at 42 and going up to, 9,999, and likewise starting at 40 and going up to some extremely large number as well. And then you'll get two answers for those, and of course you'll do your division. So that's pretty straightforward. Let's have a look at the book. Yeah, the book doesn't actually give the probabilities for those. I'm going to skip it here as well for the moment, but you can check it on your calculator that you should get out the answer of 0.716, so just under 72%. Okay, so in the last part, it says, determine if the events L is greater than 42 and L is greater than 40 are independent. Okay, now remember, if things are independent, let's get rid of everything for a moment, then you'd be saying, well, if A is independent of B, then the probability of A won't be affected by the fact that B has already happened, given that B has happened. So this is a test for independence. If this is true, then they are independent. If it's not true, then they are not independent. And the second test for independence, or sort of an equivalent test, would be to say that the probability of A and B, or intersection B, is the same as the probability of A times by the probability of B. They're the same thing, okay? But for us in this case, either or you could use. In fact, perhaps you can see that they're not going to be independent straight away from this one, because you can see that for us, the probability of the two things happening is the probability that L is greater than 42, and the probability that A is greater than, probability of A happening is just the probability of L being greater than 42, and the probability of B happening is the probability that L is greater than 40. Okay, now unless probability that L is greater than 40 is equal to 1, you can see that clearly the two things are not going to be the same. So we are not going to have two equivalent answers here, since we can see that PL is greater than 40 is not equal to 1. And that's a sufficient answer in this case. The book answers slightly differently. The book does it via this method. It says, well, look, the probability of A is the probability that L is greater than 42. And this we worked out from the previous part of the question, which is clearly not the same as this. Therefore, again, they are not independent. That's what the book says. Okay, events are not independent. Okay, well, there's a few more key examples in the book. I'm not going to go through them all. I think example 12 is good again. You can have a look at this one. It's about weights of cauliflowers. I think that's the last one that takes you up to the exercise 13D. Obviously, make sure that you are getting maximum practice on this, and know that a lot of these questions will turn into maybe we'll take into account other distributions within the question. So for example, let's have a look at question 6. This one talks about electronics company produces batteries with a lifespan that is normally distributed with a mean of 182 days and a standard deviation of 10 days. Find the probability that a randomly selected battery lasts longer than 190 days. Straightforward. You can just go and use your calculator for that. In a sample of 7 batteries chosen for quality control inspection, find the probability that no more than 3 of them last longer than 190 days. So that's another one of those questions where they're taking the probability from the normal distribution from part A, and then they're applying this one in part B in the context of a binomial distribution. Because here we're talking about 7 batteries, so we're talking about 7 trials, and either success or failure in each of those cases, either more than 3 of them in each of those cases lasting for longer than 190 days. Okay, right. So I'm going to stop there. So thank you for listening. And I think after this, we go on to, let's just have a little look. We go on to the central limit theorem. Oh no, so mean and variance of transformed and combined random variables comes next. And then I think at the end we have the central limit theorem, which then relates to chapter 14 as well. Okay.